May I now invite Chen Yikai from the Chinese University of Hong Kong for his talk towards precise reporting of cryptographic misuses.
Yeah, hi everyone. Welcome to the talk towards precise reporting of cryptographic misuse. My name is Yi Kang, and from the Chinese University of Hong Kong. And this is a joint work with my colleague and my advisors. So to begin with, cryptography plays a vital role in software security nowadays, and developers list a range of security functionality powered by cryptography. Usually, they rely on established API, such as Java cryptography architecture with the providers, or some widely used C libraries like crypto. However, the API design allows developers use them flexibly. So if developers don't know much about basic cryptography, they may use them incorrectly. For example, they may use some hardcode value for the key or individual vectors in encryption. So this is a very common problem. So it has been studied a lot in the past decade. CryptoLean is the seminal work to propose 6 rules for cryptographic misuse detection in Android applications. And later, CryptoRex reinforced the same 6 rules for cryptography misuse detection in IoT devices. And ConnectCrypt and CryptoGuard are 2 new detectors that aim for higher precision detection in Java and Android applications. So among them, CryptoRes, ConnectCrypt, and CryptoGuard are open source. They can be regarded as state-of-the-art detectors for IoT and Android applications. So to understand how well this detector perform, the researchers also craft several benchmarks. The benchmark results show the detector high precision. At the same time, the empirical results from their paper show there are plentiful violations found in viewer applications. Well, it's known that if bug detectors report too many false alarms, developers will refuse to use them. So our study is to investigate whether the violations are actual cryptography misuse or just false alarm. So for the evaluation, we connect 2 data sets. For CryptoGuard and ConnectCrypt, we connect over 3,000 applications for FJoy. And for CryptoRes, we connect over 1,400 images from 7 vendors according to its paper. Then we run the detectors on this data set and to generate the alarms. We merge the alarms based on reported misuse method because it's too much, and sort the merge alarm by their occurrence in applications, and finally analyze the root cause of top 10 of any method. Additionally, we will sample some alarms by choice. So here's the overview of our result. The main observation is that there is a gap between misuse alarms and actual vulnerabilities that can be fixed by developers. We classify false alarm into 2 types, false positive and effectual true positive. False positive are caused by implementation bugs or limitation of state analysis. And effectual true positive are regarded as true positive from the perspective of program analysis, which means that it finds what it's designed to find. However, they are ineffectual alarms because developers cannot do much to remove these alarms. And ITP may come from imprecise modeling of rules, value usage contests, or some standard mandates. We conclude 19 false alarm patterns in our paper. So due to time limit, we present some of them here. And interested reader can read our original paper for more details of the patterns. So the first interesting pattern would be CryptoGuard's non-existent data flows. So it may contain some broken diffuse chains due to variable reassignment. So here is such an example. CryptoGuard want to check whether the key store password is a constant value or not in line 10. And its data flow analysis is based on the Java intermediate representation code, Jumpo. So here is the Jumpo code of pre-release show code. And at the start, the analysis will add the object for the password parameter R5 into the use set. And later, alpha is assigned by R2, so R2 will be added into the use set. And continue backward, R2 is assigned by the R0.pwd, so R0.pwd will be added into the use set also. However, R2 is still kept in the use set. So another assign statement at line A will edit the return value of get default type into the use set, which is a constant string, JKS. So this raises a false positive for checking constant key store password. So to estimate the global scale of this type of false positive, we implement a refinement on cryptograph. So the analysis remove a variable once it meets the closest assigned statement. And to avoid overkilling, we union the use set from different branches and merge points. And we run the refined cryptograph with the same configuration on the data set, and a comparison result show that this pattern causes a high rate of false positive. We also find other problems about checking constant value in ConnectCrypt and CryptoRex. So this is such an example. And the code uses secure random to generate key store password, while it is regarded as violation of rules by ConnectCrypt. The root cause is that ConnectCrypt's data flow analysis wrongly assign the right-hand side value of this initialization statement to the local array variable. So this makes the condition of checking hardcode array always return true and cause this false positive. To conclude these false positive problems, we find that sometimes detectors process the IR mistakenly. And we believe this problem can be better found via thorough testing based on sufficient sampling of real-world applications. When it comes to ineffectual true positive, modeling of rules is tricky. So in backlist modeling, some detectors may adopt the requirement that exceeds the minimum requirement. For example, ConnectCrypt consider 1,000 iteration count insecure for password-based encryption. And both ED2551 and ECDSA 384 will be considered as misuse by cryptograph, as it requires EC key size to be at least 512, which is much larger than the requirement for RSA. We also find that the default key size on Android for EC is 256. So cryptograph also assume constant C makes output of secure random predictable. However, after we test the behavior in Android, we find that a gift C is used as a supplement to randomness in Android 7 and later versions. Older versions depend on the choices of provider, and the details can be found in our paper. On the contrary, wireless modeling could also easily cause ineffectual true positive. For example, cryptograph requires the session parameter to influence the return value of this verified method via def-use relations. However, an ITP example would be the session parameter influence the return value via control flows without any def-use relations. So there are other problems in wireless modeling. ConnectCrypt requires all the initial vectors must come from secure random. But this is unreasonable under decryption mode. And it also requires key materials to construct security keys that must come from existing security key or key object. And developer actually may load the bytes from key files or network and generate the byte array from secure random. So for the modeling issue, we recommend the detectors to justify the adopt lower bound by citing the standard of the time. And backlist modeling sometimes cannot capture sufficient conditions. And labels of confidence for different conditions by showing the data flows can better communicate with developers. Also, wireless modeling is actually hard, as it requires the understanding of common legitimate patterns. And to better understand such common patterns, mining and testing code repository can be helpful. And this is other root cause for ineffectual true positive is the context problem. So all three detectors consider any usage of ECB mode insecure. In fact, developer can only use the ECB API as raw AES block cipher for implement other secure mode of operation. So here is such an example. Google's Teen library uses ECB to implement EX mode for AES. And CryptoGuard and CryptoRex consider any usage of long cryptographic secure pseudo-random number generators insecure. Actually, developers may use long cryptographic secure PINGs in necessary scenario where it provides a desirable performance. Like here, Android source code use math random for AI UI animation. And also, CryptoGuard consider any usage of condition-prone hash function insecure. For example, MD5 can be utilized for hashing files as an index for local cache or just for login purpose. So this is an ITP example that Facebook's SoulLider library uses MD5 to hash the files that fail loading. And to summarize, ineffectual true positive come from legitimate usage contexts where they provide sufficient guarantees and desirable performance. And we recommend detectors better target specific usage that are truly vulnerable under a well-defined threat model. To better understand the generalizability of the false alarm patterns, we also evaluate them on one industrial open source detector, FindSetBug. And there are two main observations. First, file patterns are also generable to the detectors. And second, actually FindSetBug avoid detecting static initial vectors under decryption mode, which shows that the decision boundary in static detector can be tightened. Here is the takeaway. Although previous detectors did a good job in identifying potential misuse, the detectors still exhibit many unnecessary false alarms in our viewer evaluation. And the false alarm patterns come from the imprecision of statements, cross modeling of cryptographic misuse, and overlooking usage context. And for future work, we recommend the detectors to tighten the decision boundary and thoroughly scrutinize viewer result on top end of any method. And actually, we find that use viewer patterns can help refine a more precise approximation in analysis. And also, for measure the security of applications, this detector must be used with care because they have some false positive and ineffectual true positive. So our artifact is available, which include our refined CryptoGuard and verified alarms, and also some mini working examples. And I'm open to any questions. Thank you for listening.
Thank you, Yukan. It's a really great talk. So I just have a question regarding the non-existing data flows for the CryptoGuard. So I just want to make sure if I understand correctly, the non-existent data flows caused by the CryptoGuard is because the authors, they did not consider, they did not use the correct IR form. Am I right? I mean, they did not use the Jimpo IR in SSA form, so that there are the non-existing data flows that makes these mistakes, false alarms. Am I right? Just for make sure. Yeah.
Yeah. Actually, I don't know the true reason why they make this mistake, or why actually this data flow analysis can be more precise. So, and one possibility is that they implement their original data flow analysis on the static assign statement of Jumbo code, SSA form, that you will not also generate such non-existent data flows.
Oh, I see. I see. So from this code, I would say it's an IR in the 3 address format. So it's not in SSA format, but okay.
Yeah.
Thank you. Thank you for the answer.
Yeah.
Hi.
Hi.
I was just wondering, the false positive rate seemed quite high.
Yeah.
Is that viable? Is that feasible? I mean,
Yeah.
normally you want false positive rate to be very low.
Yeah, actually, when I start this research study, I assume the detectors is very precise and the false positivity cannot be such high. But actually, the comparison results show that they actually exhibit many false positive.
Right. So then, if the false positive is too high, then it may not be usable.
Yeah, right. That's the last presentation showed that usability and security are our target for the security design.